In each of 43 through 49, a sequence is defined recursively. Part A, use iteration to guess an explicit formula for the sequence, and Part B, use strong mathematical induction to verify that the formula of Part A is correct. The sequence here is u sub k equals u sub k minus 2 times u sub k minus 1. Basically, this just means that each term is determined by the multiplication of the previous two terms. So if you want to find the next term, you just have to take the last two terms and multiply them together. But that only works for each integer k greater than or equal to 2, and u sub 0 and u sub 1 are defined to be 2. Let's use iteration. This is my favorite way of solving recurrence relations. The way it works is we solve for u sub 2 in terms of our initial values here, u sub 0 and u sub 1. So according to the recurrence relation, since 2 is greater than or equal to 2, we can apply the recurrence relation. This says that u sub 2 equals u sub 0 times u sub 1. Now, I'm not going to substitute the values of u sub 0 and u sub 1, which is 2. I'm just going to leave it as is. Next, we're going to solve for u sub 3 in terms of our initial values here, u sub 0 and u sub 1. According to the recurrence relation, this is u sub 1 times u sub 2. Now, u sub 1 is one of the initial values, so I'll leave that alone. But u sub 2 can be replaced with an expression in terms of u sub 0 and u sub 1. So this is u sub 1 times u sub 0 times u sub 1, which can be rewritten as u sub 0 times u sub 1 squared. Okay, now let's do u sub 4. U sub 4 is, according to the recurrence relation, u sub 2 times u sub 3. But we have expressions for u sub 2 and u sub 3, so I'm going to replace both u sub 2 and u sub 3 with those corresponding expressions. This is u sub 0 times u sub 1, and then u sub 3 is u sub 0 times u sub 1 squared, which can be rewritten as u sub 0 squared times u sub 1 cubed. Now, the pattern's a little difficult to see here. It might seem as though the exponents are increasing by 1 here. U sub 0 went from an exponent of 1 to an exponent of 2, and u sub 1 went from an exponent of 2 to exponent 3. But that's not true between u sub 2 and u sub 3. U sub 2 has exponents of 1 and 1, and in that case, the exponent of u sub 0 did not increase by 1, which means we need to solve for u sub 5 in terms of u sub 1 and u sub 0. U sub 5 is just going to be u sub 3 times u sub 4. And we have expressions for those. This is u sub 0 times u sub 1 squared times u sub 0 squared times u sub 1 cubed. And if we combine these factors, we get u sub 0 cubed times u sub 1 to the 5th power. Notice how u sub 1 didn't increase by 1 here, it increased by 2. Now, I would say the pattern is still a little weird. And so, now I would say most students can't really identify the pattern at this point. So let's do u sub 6. I know normally we only go to the 4th term, but this pattern is a little bit more difficult to notice. According to the recursive relation, this is u sub 4 times u sub 5. This is u sub 0 squared times u sub 1 cubed times u sub 0 cubed times u sub 1 to the 5th, which is u sub 0 to the 5th times u sub 1 to the 8th power. Now, if you don't see the pattern, I don't blame you, because the pattern is pretty difficult to see here, and it would only be recognizable if you've seen this pattern before. But I'm noticing that the exponents for u sub 1 follow the Fibonacci sequence, which is just to say that each exponent is determined by the sum of the previous two exponents. And the same is true with the exponents of u sub 0. U sub 0 also tracks with the Fibonacci numbers. The Fibonacci sequence is 1, 1, 2, 3, 5. So if I were to guess what u sub 7 would be, I would say it's u sub 0 to the 8th power times u sub 1 to the 13th power. And you can double check this. This is correct, which means now we need to start generalizing some stuff. And I think it's important here to generalize before you substitute u sub 0 and u sub 1. In general, u sub n is just u sub 0 to some number, we'll talk about that exponent, times u sub 1 to some number. The first exponent is a Fibonacci number, but which one? Well, in the Fibonacci sequence, f sub 0 is 1, and f sub 1 is 1. So here's just the beginning of the Fibonacci sequence. What I'm going to do is I'm going to try to draw a relationship between the value of the index here and the corresponding exponent. Let's start with u sub 0. When the index is 2, then the exponent to u sub 0 is the first Fibonacci number, which corresponds to f sub 0. And then when the index is 3, we get the second Fibonacci number, which corresponds to f sub 1. So whatever the index value is, it looks like the exponent to u sub 0 is f sub n minus 2. So that if the index is 3, then we would use f sub 1 here, which that index is 2 less than this index. Now for the other exponent, when the index is 3, the exponent of u sub 1 is f sub 2. The index here for this Fibonacci number is 1 less than the index of u. So this exponent will be f sub n minus 1. And then we can substitute our values for u sub 0 and u sub 1. Both of these are 2. So u sub n is just 2 to the f sub n minus 2 times 2 to the f sub n minus 1. We can simplify this by adding the exponents together to get 2 to the f sub n minus 2 plus f sub n minus 1. Now, the way the Fibonacci sequence is defined is that if you add any two consecutive Fibonacci numbers, then you'll get the next Fibonacci number. So here we have the sum of two consecutive Fibonacci numbers, so we can rewrite this as 2 to the f sub n. So this means that u sub n equals 2 to the f sub nth power. And this formula works for all n greater than or equal to 0. So this actually works for u sub 0 and u sub 1. And we're actually going to show that when we get to part B. So this is the answer to part A. Let's move on to part B, where we will verify the correctness of this formula using mathematical induction. Now, to prove the correctness of this formula, we're going to use strong mathematical induction. The recursive definition of the sequence tells us that each term is determined by the previous two terms. Now, in previous videos, I mentioned that in strong mathematical induction, the number of base cases is usually the gap between the smallest index and the largest index in the recursive definition. In this case, that gap is 2. And on top of that, we're given two initial values. With this information, we should prove two base cases so that we can utilize the inductive step appropriately. Now, this formula here is going to be our P of n. Let's start with P of 0. P of 0 says that u sub 0 equals 2 to the power of f sub 0. Now, we need to prove that this is true. U sub 0 on one hand is given to us. It's 2. And on the other hand, 2 to the f sub 0, f sub 0 is the first Fibonacci number, which is 1. And 2 to the 1th power is 2. So since these values are the same, then that must mean that P of 0 is true. We'll do the same for P of 1, which says that u sub 1 equals 2 to the f sub 1. Now, on one hand, u sub 1 is given to us. It's 2. On the other side of this equation, 2 to the f sub 1 is 2 to the 1th power. F sub 1 is also 1, and 2 to the 1th power is 2. And so once again, these two are the same, which means that P of 1 is true. Now, since this is strong induction, we're going to let k be an arbitrary fixed integer, with k being greater than or equal to the largest base case, which is 1. And assume that for all I in the range from 0 to k, keep in mind 0 is the smallest base case, P of I is true. So let's detail our assumptions here. We're assuming that u sub 0 equals 2 to the f sub 0. We're also assuming that u sub 1 equals 2 to the f sub 1. But then we just keep going until we get up to u sub k, which equals 2 to the f sub k. Now, we're not going to need all of these equations to prove the inductive step. We want to show that u sub k plus 1 equals 2 to the power of f sub k plus 1. That's the goal. And to prove this, we're going to need u sub k specifically, but we're also going to need u sub k minus 1. So if you notice, I put ... here. Now, depending on what k is, this means that we could have a list from like u sub 0 to u sub 1 to u sub 2 to u sub 3 to u sub 4, all the way up to k minus 3, k minus 2, k minus 1. And the very last equation that we get in the inductive hypothesis is u sub k equals 2 to the f sub k. We're not going to need all of these, but we're going to need 2 of these. So let's prove this. We're going to start with u sub k plus 1. Now k is greater than or equal to 1. Let me make a side point here. K is greater than or equal to 1. If we add 1 to both sides, that means that k plus 1 is greater than or equal to 2. And that's precisely what we need to show, is that this index is greater than or equal to 2 so that we can apply this recursive definition. The recursive definition tells us that each term can be determined by the product, the multiplication, of the previous 2 terms. So that means this u sub k plus 1 is just the product of u sub k minus 1 times u sub k. That's the multiplication of the previous 2 terms. Now, our inductive hypothesis tells us information about u sub k. The reason why we can't use normal mathematical induction here is because we don't just need u sub k, we also need a formula for u sub k minus 1 if we want to finish this inductive step. Strong mathematical induction will give us equations for both of these, which makes strong mathematical induction a little bit more useful here. So on one hand, u sub k equals 2 to the f sub k. But on the other hand, in these ... since k minus 1 is also one of the numbers in this range from 0 to k, that means that in these ... is u sub k minus 1 equals 2 to the power of f sub k minus 1. And this we're also going to need to substitute here. So I'm going to use substitution to rewrite this as 2 to the f sub k minus 1. And then the second factor here is 2 to the f sub k. And now we can simplify from here. We can combine these factors of 2 by adding the exponents together to get 2 to the f sub k minus 1 plus f sub k. And since, according to the definition of the Fibonacci sequence, if you add 2 consecutive Fibonacci numbers, you'll always get the next Fibonacci number. Here we have the addition of 2 consecutive Fibonacci numbers. So this simplifies to 2 to the power of f sub k plus 1. And this is what we wanted to show. We wanted to show that u sub k plus 1 equals 2 to the f sub k plus 1. Now we use the inductive hypothesis precisely at this equal symbol. So we should clarify to the reader that we're using the inductive hypothesis. But keep in mind that p of k here is not enough to solve this problem. We also need p of k minus 1, which is why strong mathematical induction is required. And also keep in mind, since we're using 2 pieces of the inductive hypothesis here, then we're going to need at least 2 base cases. So this further justifies why we need to prove 2 base cases instead of just 1. Anyways, this proves that p of k plus 1 is true, which means that by strong mathematical induction, p of n is true for all n greater than or equal to 0. Thanks everyone, and I'll see you in the next video.